Hello everyone, I am Nirmith Kumar Mishra, Assistant Professor in the Department of Aeronautical Engineering. I welcome you to the course UAV Design. In today's lecture, we'll see the design criteria, objectives and priorities of UAV design. UAV design system considerations. It is a process of UAV configuration, which is a design which begins with identifying system level design considerations, definition of a need at the system level is a foundation for determining customer requirements and developing design criteria. The design criteria serve as design to, which is a requirements and can be expressed in qualitative and quantitative terms. These requirements form the boundaries within which designers operate during the iterative process of synthesis, analysis, and evaluation. Example: a UAV designed for agriculture monitoring needs system requirements for long flight endurance and camera as a payload and autonomous navigation to efficiently survey large fields. Here in the image, we can see a drone is being used to survey this crop field, and the user is having a navigation system through which he is observing the crops. The system requirements must describe both operational and maintenance support functions. Operational function refers to mission execution, while maintenance function ensures UAV availability and reliability. A well-defined mission profile is crucial to establishing the UAV's system level requirements. For example, a delivery drone requires system requirements that define its payload capacity. Example, 5 kg is the payload which it has to deliver from one place to another place. Suppose place A and place B, it's a distance between A and B is 10 kilometers, and it should also have an obstacle avoidance system for safe navigation. Right. For example, point A to point B, when it is delivering with 5 kg, we are assuming the distance is 10 kilometers. UAV designers prioritize different factors based on their objectives and mission requirements. There are three primary groups for UAV designers. The first one is military UAV. They focus on stealth, endurance, and high performance. For example, the MQ-9 UAV is designed for long endurance, intelligence, and strike missions, and it also prioritizes stealth and advanced surveillance capabilities. The second category is civil UAV designers. Here, the designers emphasize the cost effectiveness, safety, and aesthetic appeal. Example, aerial photography drones like the DJI Mavic prioritize camera stabilization and user-friendly operation and affordability. The third category is home-built unmanned air vehicle designers. They prioritize on low cost, ease of assembly, and availability of materials. Example, a DIY fixed-wing UAV for hobbyists may use 3D printed components and off-the-shelf electronics to keep low cost. Designers consider 10 key figures of merit. First one, production cost. It's a major factor for civil and home-built UAVs. For example, a consumer drone like DJI Mini is designed to be mass produced at a low cost to reach a wider market. Second category is AV performance, air vehicle performance, the highest priority for military unmanned air vehicles. Example, the RQ-4 Global Hawk is designed for high altitude, long endurance reconnaissance missions. Third category is Flying qualities. It's essential for all UAV categories. Example, a racing drone is designed for high maneuverability and stability at high speeds. Fourth figure of merit is design period, which affects time to market. Example, during the pandemic COVID-19, which led to a fast-track development of UAVs for medical supply delivery. Aesthetic appeal or intimidation factor. It's an important for civil and military UAVs respectively. Example, a commercial drone for videography has a sleek design, while a military UAV may have an aggressive appearance to deter the threats. Maintainability ensures long-term operational capability. For example, modular battery and propeller designs in commercial UAVs facilitate quick replacements and reduce downtime. Producibility relates to manufacturing feasibility. Example, UAVs with 3D printed components and CNC machinings are easier to mass production. UAV weight, which influences payload capacity and endurance. Example, a lightweight unmanned air vehicle with carbon fiber construction can achieve longer flight durations. Disposability. It's relevant for specific military and reconnaissance UAVs. For example, small disposable UAVs like ALTI US 600 are designed for one-time use in battlefield reconnaissance. Stealth capability, a primary concern for military UAVs. The BAE Tarnais used stealth coatings and a low radar cross-section design for evading detection. The design objectives: inexpensive in market. The UAV should have minimum cost so that it is affordable in the market, which is based upon manufacturing cost. Units to measure this objective is dollar or rupees. Inexpensive in operation. The second objective, it should be low cost in operations, and that will have measure based upon operating cost, how much fuel is being consumed, like how much fuel is required per liter, how much fuel is required per kilometer in terms of liter. It should be lightweight so that it can easily maneuver. It should be small in size so that such that the design is compact and which will be measured based upon its geometry, dimensions. It should be high speed for speed of operations, for having a very good performance. Maintainability, it should be easy to maintain in a minimum cost. Producible, it should require technology for manufacturing and it should be easy for manufacturing and production. Recyclable, it shouldn't impact the environment. Ninth objective is maneuverable. Here, when it comes to the turning of the aircraft or climbing of the unmanned air vehicle or diving of the unmanned air vehicle or performing any primary or secondary operations here, the movements here, it should be easy. It should be agile in nature. Detect and avoid, it should have navigation sensors, and during its flight, if there are any obstacles during the flight, it should detect it and it should avoid its collision with that obstacle. Airworthiness, it should have basic safety standards as per FAA, FAR, or if it is operating within India, so it should have DGCA approvals. Autonomy, it should have autopilot complexity where crash worthiness or formation flight is measured. Early in the design evaluation process, a baseline is established to compare different design configurations. This baseline is defined through iterative analysis of identification of mission needs, feasibility analysis, definition of operational requirements, selection of maintenance concepts, planning for phase out and disposal. The mission scenario must be described, including expectations for cycle time, frequency, speed, cost, and overall effectiveness. This is an example of unmanned air vehicle for disaster response, which may have a baseline requirement of 30-minute deployment time and ability to operate in extreme weather conditions. These are design priorities. As a designer, these figure of merits will have priorities. 1 is high priority and 10 being least priority. So, depending upon the designer, depending upon the requirements, these priority varies. Cost is at 4, performance is priority number 1, autonomy is priority number 2, stealth is priority number 3. Stealth is priority number 3 only for military UAVs. Military UAVs. For civil application UAVs, stealth is not required. Stealth is not a priority. Here it can be marked as 0 for civil applications. 4th is cost. Then period of design is 5. Producibility is 6. Maintainability is 7. Weight is 8. Disposability is 9. And scariness is 10. Scariness is how it looks. Scariness is about how it looks. So, here you can see an example of designer 1, designer 2, designer 3 in their percentage. Some of the designers, if we take an example of designer 1, he has given preference for the performance 50%, 10% to autonomy, then 8% to the cost, 7% to the period of design, 6% to producibility, 4% on maintainability, 3% to the weight, disposability 2, stealth 9, scariness he has given as 1. Right? So, sum together these percentile should be 100%. If it is a military unmanned air vehicle, then automatically this will be 1, performance will be 1, autonomy will be 2, stealth will be 3rd. In this case, stealth has been given as 11%. In this case, it is 12%. So, basically, any unmanned air vehicle, whether it's a military or a civil application, performance will be high priority. Optimization objectives help in selecting the most suitable UAV configuration. UAV optimization typically considers a single primary objective at a time. Applicable design criteria should be expressed in terms of technical performance measures. TPMs represent quantifiable attributes inherent in the design, forming the basis for performance evaluation. It is essential to distinguish between design dependent and design independent parameters for holistic approach to unmanned air vehicle design. For example, an agricultural UAV optimization may focus on maximizing flight time while balancing payload capacity for multispectral cameras. You can see cameras here. Conclusion. UAV design is a complex iterative process that balances multiple competing factors. Prioritization of design criteria varies among military, civil, and home-built UAVs. Establishing a clear set of technical performance measures and optimization objectives is critical for achieving an efficient UAV design. Understanding system design considerations helps engineers developing UAVs that meet mission requirements effectively and efficiently. Example, the NASA's Ingenuity helicopter on Mars, which was designed with strict weight, power and communication constraint, demonstrating how UAV system design principles apply even in extreme environments. With this, we can